In this video, we continue with application problems on the normal distribution. So, for the next example here, we are told that steel rods are manufactured with a mean length of 25 centimeters. Because of variability in the manufacturing process, the lengths of the rods are approximately normally distributed with a standard deviation of 0.07. So the lengths of the rods, that would be our x, which are approximately normally distributed with a mean of 25 centimeters and a standard deviation of 0.07. Question A. What proportion of rods has a length less than 24.9 centimeters? So using the distributional properties, we have the mean of 25. We have the standard deviation of 0.07. We're interested in the region less than 24.9. So I'm going to locate 24.9, which is zoom on. Then for less than 24.9, that will be the region below. So I'll go to Start Crunch. And here we go, going to Start Crunch. And I want the region. I want to set up the parameters first. What are the parameters? The mean is 25. The standard deviation is 0.07. So 25 and 0.07. And we want less than or equal to what value? Again, less than 24.9. So I am going to write 24.9 here and enter. So you have 0.0766. 0.0766. So this region is equal to 0.0766. This is probability of x less than 24.9. Then for the next question B, any rods that are shorter than 24.85 or longer than 25.15 are discarded. What proportion of rods will be discarded? Proportion that will be discarded will be equal to the proportion where it is shorter, that is lesser than, where the length is lesser than 24.85 or longer than, that means combined with those whose lengths are longer than 25.15. So in my visual, drawing the normal distribution, I have 25 here. I'm going to locate 24.85 and I'm also going to locate 25.15. I'm interested in the region above 25.15 and below 24.85. So let us do that. So for the first part, let me see the size of this region. And I will go back here. I'm going to change this to 24.85. And I have this size. So now that I have the size of this area or that probability, I'm going to go ahead and find the size of this other area. So let's do that. Going back here, I'm going to change this to greater than or equal to 25.15 and hit the enter button. And I have 0.1606229 again. So going back, I have the same number again. So now that I have the sizes of the two areas, I'll combine them. And when you add them together, you should have approximately 0.0321 to 4 decimal places. Then for question C, using the results of part B, that is this result, if 5,000 rods are manufactured in a day, how many should the plant manager expect to discard? This is the proportion or the fraction of all of the number of manufactured rods in a day that should be expected to be discarded. So this question is simply a matter of multiply the proportion by how many rods were manufactured that day. So multiplying that, we have 0.0321 times 5,000, and that will be equal to 160.5. Well, if we want to round this to the nearest integer, it should be approximately 161 rods to be discarded based on historical data evidence. Then question D. If an order comes in for 10,000 steel rods, how many rods should the plant manager manufacture if the order rather states that all rods must be between 24.9 centimeters and 25.1 centimeters? Well, the first step 1 in this case, is to find the proportion of rods that are between 24.9 and 25.1. So going into this, you have this part, you have 25 in this case, you have 24.9, and we have 25.1. And so we want the region between them. And as it stands, this will be equal to, going back to StatCrunch, I'm going to change the interface to between, and I want between 24.9 and 25.1, I believe. Let's check that again. 24.9 and 25.1. Yes, that is correct. So let's compute the proportion. The proportion here is 0.8469. Okay, so let's take that here, 0.8469. Now that we know the proportion, so about 84.69% would be in this range. Well, we have just gotten an order for 10,000 steel rods. So regardless of, let's think about this together. Let's see how many rods to be manufactured. That is the question here. How many rods should the plant manager manufacture if the order states that all of these rods must be between this dimension? So this is what we don't know. We do know that no matter the number of rods we produce, this percentage would be in this range. And we expect that number to be 10,000. So as it stands, I am saying that 0.8469% of no matter the number of rods we want to produce, I'm going to let that number of rods be equal to R. So this percentage of total rods produced must be equal to meet the order demand with the right specifications. So with that said, let's see. So what would our R be? We need to divide both sides by 0.8469, 0.8469, and so you have, this takes out this, and you have R is equal to 10,000 divided by 0.8469. This will be equal to 11,807.76951. This will be approximately 11,808 rods. So this is what we advise, because we know that when we take this fraction of this, we will get 10,000 that will have this specification. With that question completed, we proceed to the next example. In this example, the time required for Speedy Lube to complete an oil change service on an automobile approximately follows a normal distribution. So this time, the random variable x is the time required to complete an oil change. And it has a normal distribution with a mean of 17 minutes and a standard deviation of 2.5 minutes. Question A. Speedy Lube guarantees customers that the service will take no longer than 20 minutes. If it does take longer, the customer will receive the service for half price. What percentage of customers receive the service for half price? So percentage of those who are paying half price will be the percentage of those whose time required or time used to complete their oil change was what? Was more than 20 minutes. Because once your time for changing the oil takes longer than 20 minutes, you are receiving a half price. So this, in the context of the problem, follows the normal distribution. The mean is 17. We're finding a probability connected with the number 20. And in particular, we want to find the size of the area to the right of 20. So this will be equal to, let's see. So we want the parameters, and I want a standard interface. The parameters in this case are 17 and 2.5. 17 and 2.5. And I want the area greater than 20. So I'm going to set that up. So I want greater than 20. Enter. So I have 0.1151. 0.1151. This is the proportion. The question wants the percentage. So we might multiply this by 100%. That gives 11.51%. Then, question B. If Speedy Lube does not want to give the discount to more than 3%, that means that's the upper bound of its customers, how long should it make its guaranteed time limit? So, this is a management decision using data. So, in this case, we're looking at the whole distribution of all the time for service or service time. You have the mean, which is 17, and we want to find a value that a number that the proportion more than that number is exactly 3%. So 3% here, or 0.03. What is that number? Remember, this is our X, the time, the service time. So there is a particular number here that, based on historical data, if we set that number as the guaranteed time limit, we will only be giving discount to 3% of our customers, because only 3% of these customers would have a service time approximately longer than this unknown time. So how do we find that? We use inverse normal distribution. So I'm going to go back. I have the mean. I have the standard deviation. I'm going to delete this. I'm going to change this to 0.30. Make sure that, since the picture indicates that this is the area to the right, or the greater than, that you indicate that this should be greater than, and then compute. So 18.31. So in this case, I have 18.31. And in what measure, or what units are the time measured? It's in minutes. So we want it 18.31 minutes. This is what should be made the guaranteed time limit. With that question completed, we proceed to the next example. The ACT and SAT are two college entrance exams. The composite score on the SAT is approximately normally distributed with a mean of 21.1 and a standard deviation of 5.1. The composite score on the SAT is approximately normally distributed with a mean of 1026 and a standard deviation of 210. Suppose you scored 26 on the ACT and 1240 on the SAT. Which exam did you score better on? justify your reasoning using the normal model. Okay, so this is what we do. We're going to draw a line between the ACT exam and the SAT exam. For the ACT, the mean is 21.1 and the standard deviation is 5.1. And we're told that that distribution is normally distributed approximately. So X, your score on the ACT is normally distributed with a mean of 21.1 and a standard deviation of 5.1. Whereas on the SAT, it is also normally distributed. I'm going to let this be Y with a mean of 10.26 and a standard deviation of 210. Okay, so suppose you score 26 on the SAT. What I need to note is that if I look at the distribution of the SAT scores, you have 21.1 in the middle, and then we have 26. So 26 is somewhere here. My interest here would be to find the region below, the size, how many people scored lesser than me. So in this case, this is the percentile. I'm trying to find the percentile of 26. So probability of X less than 26, going to StatCrunch, I'm going to key in these parameters, 21.1 and 5.1 for the standard deviation. So going here, we have 21.1 and 5.1 for the standard deviation. And I want the region less than or equal to 26. So less than or equal to 26, hit compute. So I have this at about 0.8317. So 0.8317, that will be approximately 83.17%, or approximately the 83rd percentile. That is where 26 sits. Okay, what about the SAT score? Suppose you scored 26 on the ACT and 1240 on this SAT. So again, for the SAT, it also has a normal distribution. The mean is 1026 and you scored, or I scored, 1240. So 1240 is somewhere here. Again, similar to the argument we introduced earlier, we want to find what percentile that 1240 is compared to other test takers. So you have probability of X less than 1240. That is what we want to find. We'll set up the right parameters, 1026 and 210. So going back here, 1026 and 210. We want the region lesser than 1240. Again, take note, the region lesser than 1240. So back here, we compute that. This is 0.8459. Okay, so 0.8459. Just to confirm, let's check that again, 0.8459. So this is approximately 84.59%. This sits at about the 85th what percentile. With these two indicators, using the normal model, we can justify that on which exam did you score better. Well, since you sit on the 85th percentile here, which is higher than the 83rd percentile, we can, based on this data, say that you performed better on the SAT. You performed or scored better on the SAT exam. So there lies a very good application instance of the normal distribution and how it is used in ranking processes.